Welcome back. And what we're going to do now is we're going to look at the recursive types. When we looked at type synonyms, we tried to declare a recursive type synonym, but we noticed that that didn't work. And then I explained that when you want to create a recursive type, it has to go via nominal type. And what we're going to do in this part of the lecture is we're going to look at a few recursive types. And the recursive type that we're going to look at first is the type of natural numbers, of integers. If you recall the lecture on recursive functions, what we did there when we defined a function by a recursive function over integers, we said, well, an integer can be either 0 or it could be, the successor of an integer. And since we don't have n plus k patterns anymore in Haskell, we would have to write n minus 1 on the right-hand side. But if we represent integers in this way, we can write nice recursive functions on these two cases. It's either 0 or the successor of a natural number. All right? So a natural number is either 0 or it's one more than another natural number. And if you look at the types of the constructors, 0 is a function that takes no arguments and returns a natural number. And suck is a function that takes a natural number and returns another natural number. So that's the types you see there on the bottom. Okay. So if we look at all the values of this type suck, you will see that it starts at 0. That's the base case. Then we have suck of 0 and suck of 0, etc. I mentioned before that we're kind of glossing over certain details here, because one of the values that we can also have is undefined. But since we're, just an introductory course, I'm not going to talk about undefined and bottom. So for now, and typically it's perfectly safe to do. This is the kind of, infinite set of values in type net. And as I said, this recursive type represents numbers. And what we can do is we can take an instance of this net type and map it to an integer. And the way we do that is we can turn every occurrence of the suck constructor into 1 and every occurrence of 0 into 0. And you see that we maintain the same structure and we add those up and we get 3. So what we can do is you see that this is a homomorphism from net to integers, and we can define that just like we defined fold R over lists. We can define this function using fold R over natural numbers. For now, we're going to do it recursively. So here is a function that goes from net to int. So net to int of 0 is 0. And net of int of n plus 1 is net of int of n plus 1. And we can go the other way around. If we get an integer, we can get a natural number. 0 becomes 0. And here you see where I miss n plus k patterns. N becomes the suck of int n minus 1. So it would be not much nicer if this would be n plus 1 is the suck of int to not of n. But, we have to respect the decisions that the Haskell, current Haskell committee makes. Okay, now what you can do is you can try to prove that these functions are inverses, and then you can show that net is isomorphic to int. And of course, we're shoveling the fact that there's bottoms involved here under the carpet. Given two naturals, we can add them up by first converting them to integers and then converting them back to nets. That's kind of, pretty brute force, right? So we have these natural numbers. We're going to convert them to integers, add them up, and then convert the result back. So we take a natural number, convert it to an integer, take the other one, convert it to the integer, add them up, convert it back. That's not very efficient. So instead, we can define this directly by induction over the natural numbers. So if we add 0 to n, that's the same as n. And if we add m plus 1 to n, well, that is m plus n plus 1. And that's the definition that you see here. So I think this one is much more elegant than this one, but they are equivalent. If we execute an example, so we want to add 2 to 1, let's see. We recursively push the addition inside and take one of these sugs outside. We do that several times. So you see that the add gets pushed inside until it hits the 0, and that's 0. And there we go. If we add 2 plus 1, we get 3. Great. So that was the end of part 2. And I'll see you in a few minutes where we're going to talk about type classes.